like, why are things the way they are, right? That's one of the cool things that I think, at least, about engineering. Like, why do we do things the way that we do things? Why do things look the way that they do? Why do the things behave the way that they do? And I think this is kind of a cool class where we get to delve into that a little bit, as far as at least like one corner of that. Why are things the way they are? So that's one of the things I like about fluids. So we'll try to do that a little bit this semester. Before we jump into too much, I want to make sure we have like a level playing field, that we all know what we're talking about when we talk about a fluid. And I say that because there are some things that are kind of a little bit wishy-washy, right? Like, we know solids and we know liquids and gases, but there are lots of things that don't fit nicely in boxes like that, right? Welcome to the world. What do you do with something like whipped cream? Right? Is it a solid? Maybe, sort of. But if you squish it, it's not really elastic. It kind of, if you push on it, it starts to flow and move like a liquid. So what do you do with things like that? What do you do with, right, some things, like maybe some of you have run into at some point in your life something called oobleck, where oobleck, if you push it gently, it behaves like a liquid, but if you really bang on it, then it behaves like a solid. It does its weird stuff. We'll watch some videos of that, I hope. So for fluids, and I'll post these so you don't have to feel like you need to copy everything down. But a fluid, and this is really, right, we're kind of defining a class of things by a definition that doesn't necessarily work perfectly and wonderfully for every possible thing. There is a gray area. But a fluid is something that we're looking at really this. It's something that deforms continuously upon application of a stress, of a force. So you think a solid, like I push on it, maybe it deforms and then it springs back into place when that force is removed. There's some elasticity. Like a super ball, I can squish it, but if I let go, it springs back into shape. That's what solids do. Liquids, if I push on it, it deforms, and then there is no restorative force. Now, there are things that like have a little bit of both, but generally it's continuous deformation, and that's what we're talking about with the fluid. You remove the force, it doesn't go back. It's an irreversible process. So this would be kind of the picture. We have a solid over here where we apply a force, maybe there's a deformation, but it comes back to its original shape. A fluid, we apply a force, and it continuously deforms, right? It doesn't like move and then stop. Okay, another key concept for a fluid, and we'll talk about this a lot, and you have seen it at work in the real world, and I'm assuming that nobody's ever actually thought of it this way. It's called what we call the no-slip condition. So in the world of fluids, very often, very often, we have a solid fluid boundary, right? We have like water moving along a surface. We have air flowing, over the ground. We have air flowing over a car. We have a boat going over water. All of these cases, we have some sort of solid fluid boundary. And the weird thing about fluids is they get stuck to solid surfaces. So the no-slip condition, fluids don't move along a surface. The fluid in contact with the bottom of a boat, the fluid right on the bottom, smack dab on the bottom, is moving with exactly the same velocity as the boat. If you have air blowing across the ground, the air on the ground is stationary. The air above it might not be stationary, but the air exactly on the ground is stationary. This is an experimental observation. We'll just go to a quick video just to show that in kind of an interesting setting. So there's the fluid, you can't see it, it's water, but it's moving, and you can see it once we inject dye into there. So we're going to inject dye in the bottom. You can see the fluid moving. Notice how obviously the dye above the ground, above the floor is moving, but exactly where we put that dot doesn't move until you brush it away. Right, it's not stuck there, but it does get stuck there. It doesn't slip along the surface and kind of get pushed further and further. It gets stuck on that solid surface and moves at the exact same velocity as the solid. Oh. That's fun. Okay. So the no slip condition, we'll continue to bring that up. It's an experimental observation, but it's one that, like, this is how fluids work and behave. Kind of a crazy thing. That works even for things that are moving super fast. If you have an airplane flying at 500 miles an hour, the air on the body of the airplane is stationary. The air just a tiny bit away from it is moving really fast. But exactly like where they meet, they don't slip along each other. They're moving at the same speed. Kind of crazy. Okay, last thing, gases versus liquids. Again, these are things that you know about these. The other two maybe less so, but just to have a consistent definition, right? A liquid is something, it is practically, and I'll use this word quite a bit, we use it in thermodynamics. They're incompressible, right? You push on them and they don't really change volume very much. They're not exactly incompressible, but close. A gas, obviously, you have, right, you have something, you know, if it's an ideal gas, PV equals RT. If you change the pressure, they do change volume. They expand and contract. Liquids don't really expand and contract with pressure. Gases do. And then the other thing, right, liquids have a definite volume. Right, if you have a cup of water, you have water sitting in the bottom of your cup. They often can have a free surface, meaning like not inside of a solid, whereas gases expand, obviously, to fill up whatever space you give them. Okay, so just some kind of background terminology ideas that we'll continue to bring up. I'll post the slides. You don't need to write everything. Okay. So we're going to be talking throughout the semester about fluid motion. So the way that we can talk about it and picture it and visualize fluid motion, there are different ways that we can think about it and describe it. We're going to be trying to describe it mathematically and like visually, right? So we're going to kind of try to do both of those things. In certain circumstances, it might make sense to have kind of like one picture of, or one way to talk about it. In other circumstances, maybe there's a slightly different way that we want to talk about how fluids are moving. But we want to make sure like the terminology is the same so we know what we're talking about and what we're looking at and how to describe these things. So we'll start by looking at what we call a velocity field. Okay, so this is what we're going to describe. This is the motion of a fluid. So we have a fluid in motion, and we could describe that by looking at individual particles. So we're going to put it on a coordinate system because we're going to try to describe this mathematically. So this is the y direction, that's x, we'll call that z. And we're going to look at a particle of fluid, some point in our fluid, and say, okay, where is that, how is that particle of fluid moving at this instant in time? Maybe it's moving somewhere like that. So we'll call this velocity of 1, or v1. And maybe there's a different particle of fluid somewhere down over here that at this moment in time is moving in a different direction. right? If we wanted to characterize the motion of the fluid as a whole, we would have to know every individual particle and like how fast and in what direction it's moving at that given instant, right? We would need to know the entire space. We would need to know velocity for every particle. So in general, so at time t, P1 is moving with velocity v1 and P2 with velocity v2. In general, velocity changes with position. And time. Okay, and these are really the kind of two crucial things, position and time. So if you look at fluid motion, where you are matters and time matters, right? If we looked a little bit later, maybe this is, you know, a fluid all mixing up crazy. If we took a snapshot, we say, okay, how is it moving right now? Take another snapshot, it's moving a little bit differently. We usually try to describe velocity in terms of its directional components. So we can describe our velocity vector in terms of I, j, k components. So, right, if we looked at, again, on our coordinate axes, this is y, x, z. If we have some velocity like that, right, it has right, some component in each of these different directions. Right, we're decomposing the vector into its individual directions. What we call them in fluids, and what we'll call that, the nomenclature that we'll use, this direct distance, the x distance is u, the y distance is v, and the z distance is w. So v vector equals u I hat plus v j hat plus w k hat, where I, j, and k are the unit vectors in x, y, and z. Okay, and because because v varies with t and with time and space, in general, u, v, and w also vary in those dimensions. So u is a function of x, y, z, and t. V can be a function of x, y, z, and t, and w can be a function of x, y, z, and t. Okay. Typically, we'll talk about if a flow is one-dimensional or two-dimensional or three-dimensional, if it varies with time, And we'll talk about that based on how these guys are varying. So if, let me make my notation a little bit better. If for example, V equals, and I'm just going to make something up, but it's 2xy plus 3t I hat. I'm just making up some mathematical equation for some velocity field. Say this is the velocity field. This isn't a realistic velocity field. It's just numbers that I made up. But if this is your velocity field, what it means is that there is no change in the velocity. Like as we go, the velocity field is pointing in the x direction. So all of the velocity field, wherever you go in space, is all pointing exactly in x, because that's what the I hat tells us. But it's changing as you go both in x. So if you go further in x, it's getting faster. And as you go up in y, it's also getting faster. So it's changing in x and y. It's pointing in x. It's changing in x, y, and t. So this is pointing in x, changing in x, y, t. Okay, just for one example. And we're going to have some practice with that and trying to figure out, which direction are we pointing in, or maybe 2 directions or 3 directions, and which direction are we changing in. Okay, so, all right, so we're going to have a chance. Pull out your cell phone if you have one, hopefully. I sent you an email not that long ago with the paper that you're looking at. So hopefully I sent you an email with the paper that you have in front of you. Pull up the YouTube video that I sent with in that email. And then take a few minutes, just the front side of that paper that you grabbed. We're only going to finish the front side right now. But basically, we're going to watch this video, and you're going to sketch out the velocity field at least a couple points, right? Which is the velocity field is telling you how fast is it moving and in what direction. So if it's moving faster, that's a bigger arrow. If it's moving pretty slow, that's a short arrow. And you're doing that, how fast is it moving at that given instant?
What's the time on the video?
Yeah, so the time there is the timestamp on the video. And I don't know why it says t less than 45. It should be like t equals 45 for the first one, but.
Are we drawing what it looks like? Or we
just sketch the velocity. So you're not drawing what the whole thing looks like. You can use the sound and turn sound on. I don't care. But you're just drawing the instantaneous velocity at the points that are given on your little circles. Okay, this should only take you just like a couple minutes. So there's no, there's no award for being the world's greatest drawer. So velocity vectors should be straight lines pointing in the direction of the instantaneous velocity. So they're an instantaneous, like, pause video thing, not telling you, like, it shouldn't be a curved arrow moving the way that it's going to be moving. It should be scaled to the size related to the speed. And then the direction is the direction. And it's instantaneous. So again, you don't need to do perfect. Just do what you do. Do what you can. And the first little bit, when he's mixing it up, they're not all moving perfectly in a wonderful circle. So it ends up, this is actually part of the hypnotizing technique that I have. Keep clicking on this video. So we'll take maybe 2 more minutes. And I promise I won't grade you down for being wrong, but for using velocity vectors that are like curvy or not a vector, like vectors are straight, and they point in the direction that you're going, so they should be straight. Yikes! I'm gonna break my super big TV. Okay, so I told you I'd give you 2 minutes. I think I gave you 1, but you'll be able to deal with it. Okay, right. Perfect is better than we need right now. Okay, so a couple things about the video. One, I kind of like it because it's another video in space, which I think is fun. When you watch it, though, I think it does give a good picture of a 2-dimensional flow. Right, you have the the velocity changing, I guess, in both x and y, but we could also describe that as a rotational flow, where really the velocity is only changing in r at later times, right? It's only really related to the radius. So this would actually be something that we it looks 2-dimensional, but you could pick a coordinate system in your mind that it's really only changing in 1 dimension. Okay, so that's kind of cool. At what point do we reach? So I think this was question 2. At what point in your estimation do we reach what you would call steady flow or a steady state? Right. So when he first mixes it up, it kind of swirls and whirls. At what point would it be steady flow?
120.
Okay, like 120, 130, somewhere there. So the first little bit, it's swirling and it's changing with time. And then eventually, it still is changing with time, like it's slowing down a little bit as it continues, but it's at least, you know, ballpark steady flow. Okay, so we reach steady flow. If we wanted to show that mathematically, steady flow, we could write it as dn dt equals 0, where that's not an n, it's an eta, but it's an n with a funky tail, is any fluid property. So for something to really be steady flow, all of the things have to be constant with time. So you looked at in your video, and you're correct, it was like 120, 130. You see the velocity no longer changing with time, but for it to be steady flow, the viscosity, we haven't talked about viscosity, but we will. You've probably heard the word. That has to be constant with time. The density has to be constant with time. Like all of the properties, everything has to be constant and not changing with time. Okay, so now it can still vary spatially, right? There's still a different velocity at the center than there is in the middle as at the edge. So it can still vary depending on where you are. It's just not changing in time. So it can change in space, just not time. And that's true for all of the properties. Like you can have the density change with space, but not time, and still be in steady flow. Our lives in this class, we are going to be living in the land of steady flow. Because when you start talking about things that change with time, it gets more exciting mathematically, and we're not going to really go there so much. So we'll be living in the land of steady flow, and that's okay, because that's where we'll hang out. Okay, so you described flow using like a point vector notation, right? Where you could imagine if you had put more dots on those circles and you drew a vector at each one of those dots, you'd get then a full description of what's happening, but your paper would get really ugly and messy because you would have like little arrows at every point. So we need better ways to talk about and describe how flows work rather than just like putting velocity vector arrows everywhere. So that's what we're going to do. So how do we describe flow? And there are multiple different ways. So way number one would be a timeline. So what timelines are, they're lines through adjacent fluid particles which over time show relative motion. Okay, so what would this be? This would be, you want to look at the flow, so you throw some sort of like a dye or a marker in the flow. And then you can look at like a snapshot of where how that's moving. And you said we threw it all, in right next to each other, and it moved and swirled, and some went over here and some went over here. So it's looking at like the kind of the individual snapshots. So it might be something, again, just to draw a picture. If we looked at, say, two surfaces, one surface moving and the other stopped. We haven't done this yet, but what will happen is you get a nice linear velocity gradient because of the no-slip condition. You now know the no-slip condition. So if the bottom one stopped, the fluid on that surface has to be stopped. If the top one's moving, the fluid on that surface has to be moving, and it turns out you get a linear velocity in between. If we had a timeline where, say, we started a line of some marker there, and then we watched what happened. We'd take like a snapshot there initially. After a little bit, the top has moved, the bottom still stayed still. So this would be, it would then look like that. We'd wait and take another picture a little bit later. It would look like that. It would look like that, and we could kind of build up a snapshot version of a way to describe the flow. Okay, so this is probably the least common way that we'll use, although we will use it some. Number two, we'll call it the path line. And this section of notes, I promise, will get screwed up later in this class, but we'll keep coming back to like talking about this stuff. So, because we do need common language and pictures to be able to describe that. So a path line, here's the definition. It's a path or a trajectory of a fluid particle. Okay. So it's, say we tracked an individual piece of fluid and watched where that went. We kind of did that like the chalk dust in the little swirly picture that you just did. Those were individual fluid particles. So if you took like a long exposure image of one of those particles going around in a circle, that would be a path line. So you're watching, it's like a long exposure of where one thing goes. I describe it like this, so it's like a long, exposure picture. I don't know, this is maybe not the greatest analogy, but like if you have a football team, this is the route that the receivers ran, that's the path line. So it's showing the entire path that fluid particle or that football player that they ran. Okay. Third one is a streak line. So a streak line is a line connecting particles which all flow through a common point. Okay. The example I'll give is it like die. Okay, and that maybe isn't enough explanation to understand what I'm talking about, but the video that we just watched, I just want to see the commercial again. How do I get back now? Okay, no, stop it. Okay. So in this video that we just watched, the dye coming off the syringe head is forming a streak line, right? So okay, so they put some on the bottom. Okay, so if I stop it here, the dye that's coming off of that syringe head is all originating from the same point, and then it's moving with the fluid. So all of that's a streak line. That dye path is a streak line. You're not following an individual particle. You're following fluid that all like originated from the same point. Some of these you can see the definitions kind of overlap, and you can say, well, isn't that both of them? And you're right. So we have multiple ways to talk sometimes about the same thing. So the image that I give, and this is one of the videos that we watched, was a like a hose that was connected to a speaker. Maybe you watched that, maybe you didn't. It's kind of a fun one. You should go back and watch it if you, maybe that will help you understand what streak lines and path lines are. But this hose, moved back and forth really rapidly at 24 hertz. And that caused the water to look like that. Right, which was kind of the fun part about the video. It looked like it was just frozen there because the shaking of the hose was synced exactly to the frame rate of the video camera. Anyway, but that water curvy path, that is the streak line. Okay, but if you were to follow an individual particle of water, right? Particles don't travel in these kind of crazy wavy things. They travel projectile motion. So if you were to track an individual particle, like right there, it's still going to go like that. And this one's going to go like that. And there's going to be another one that's going like that. And they're just, maybe I'll draw it a little bit better. So this one, it goes to end up like right there. This one ends up right there. This one is going there. So those are path lines. Like the projectile motion path of any individual particle, if you could like take a, have a streak that showed up of that, that would be a path line. But the wiggly stuff is the streak line. Again, there's somewhat murkiness between some of the different definitions, and I understand that. The last one that we're going to talk about, and the one that we'll talk about the most, is called a streamline. Okay, so, why do we talk about streamlines the most? We started this class talking about what if we had an XYZ coordinate system and we wanted to talk about the velocity at every point. That's what streamlines help us to do. So streamlines are lines tangent to the velocity field. Okay. Another way of saying that same thing is the velocity perpendicular to a streamline is 0, exactly 0, which is another way of saying like there is no flow across a streamline. And we'll start to put some more math and we'll come back to this again. The last part to note is the velocity magnitude can change along a streamline. Okay, so again, we'll come back to this, so I don't want to, we're not going to talk exhaustively about this right now, but if you can take your paper and flip it over to the back side, we'll finish this up. So in part 3, consider only the steady flow portion, so that like 1.5 minutes to 2 minutes or whatever it was, only the portion where things are not changing with time. And consider a particle somewhere at point P. So it starts there, and kind of show what's going to happen to that, both with the path line, a streak line, and a streamline. And I think the top one is supposed to be the path line, even though it's not labeled. The middle one should be a streak line. The bottom should be a streamline. And see if you can figure out with the definitions that we just had, what that line would look like. Try your best, raise your hand and ask questions if you have a hard time thinking of it. Okay, and then whenever you're done for this, we're done for the day. So as you walk out, hand in, this page is due like next class, but I'm assuming we'll all get done with it before we leave. So just as you're leaving, just set it on the table as you go out, and then have a great Wednesday. Yeah.
What does this streamline look like then?
So a streamline, okay, so this is a path line, so it should trace the path of that particle as it moves.
As it moves, would that mean there's multiple of these?
That, so what you have drawn is the instantaneous velocity.
Yeah.
That's important, and that's what we did on the front side. Now what we're doing is drawing a path that's tracing out.
Should we do this and we can do a curve, or can we not?
Okay. So that one you're watching.
The street line will be a curve then.
Yep. So this one, you're tracing a path line, you're taking that particle, and you're taking like a long snap exposure of that individual particle. Like imagine it was a flashlight, and you take one of those nighttime pictures, and you see like where did that flashlight move. It's going to go around the whole circle.
Yeah.
Circle.
So for the streamline, is that like?
So the streamline is,
Tangent all the time.
so tangent, so at point P exactly, what would be a line tangent to the velocity?
So if it's like this, the tangent's on the outside. Like,
Oh, that is what it is. Okay, so draw, like if you were here, tangent to velocity, tangent to velocity, velocity would be, you're kind of curving tangent to that line, tangent to this one, then tangent to the one before, and tangent to that guy.
yeah.
So the trick is that they're on the exact same.
Do you want us to draw like the whole thing? Like towards?
The whole circle.
Okay.
So there's the path line. The path line is a long exposure picture, like the nighttime picture of a highway. And you're watching like the headlights of that one car.
What about the street?
So the streamline, the streamline, you're putting new dye or something in that point P constantly. And then like waiting a while, then you take a picture.
This is it.
Yes. Perfect. So the trick is that they're the same. So we have different ways of talking about them. Steady flow. They're all You go with that.
What time are you in piano? Okay. I'm in the 10 o'clock.
So we have P. So P is, right, that would be the velocity vector. We would draw a line tangent to that. And then say over here, we have a new point. Now the velocity vector is there. New point. Now it's right there. So we would draw a line that is tangent to all of those velocity vectors.
So the streamline is always perpendicular to the particle that's moving, is that what?
The streamline is always, and again, we're going to keep doing this stuff because it's going to be important. But the streamline, which is the line here, is always tangent to the velocity at any given spot along the streamline. So if you see a streamline that's a circle, and you say, what direction is the velocity pointing in? It's pointing tangent to that streamline. So if we have some streamline like this, and we chose a point here, we could say, we know what direction the velocity is, it's in that direction. If we chose a point along here, it's in that direction.
So then what's the difference?
They're all, in steady flow, they're all exactly the same. Which is, if something is changing with time, then they will all be different. If something's not changing with time, they're all the same. So the key idea is we're going to be able to do experiments like that functional give us half lines or 2 lines. Or if we have steady flow, they'll have 2 lines. So the experiment is going to be
The experiment, right?
either 2 months, do an experiment, dye in the water, or something like that, or slow. all of those things are going to be either a path on a street line, or that's functionally. But, it's then
Yeah, I was confused again because of the ground and the circle.
Yeah, that's why I'm confused about this one, but.
so that's why, and again, this is why we're going to continue to get them mixed up. Because they're all the same, so they're also all not the same. Such as that.
I actually had a question for you.
Yeah.
How would you feel, because you record every class, right? Let me back up.